All right, good morning or afternoon. Now, today we're going to be covering triple integrals that are going to be covered in cylindrical coordinates and in spherical coordinates. And what I'm going to do is I'm going to present cylindrical coordinates first for triple integrals, and then we'll go through and we'll present spherical coordinates for triple integrals after that. All right, so the way we're going to think about these cylindrical coordinates is going to be in the sense that we want to try to make these cylinders occur. And the way we make that occur is if we choose any point out in R space 3, out in our Cartesian, out in our rectangular coordinate system. And what we want to do then is we want to transfer all of those coordinates into what we know as polar coordinates. So when we do this, every point in R space 3 can be thought of as x, y, z coordinates. Well, could it also be thought of differently? Meaning, could we have some r value that was made by some theta value, and then could we then give that some height, call it z? In that sense, what we're initially doing is we're considering this x and y plane as our polar coordinate plane, our coordinate system, and then what we're doing is we're just adding some sort of height to this. So in that sense, every single point in R space 3, instead of thinking of it as in rectangular coordinate system, we can then think of it in terms of polar coordinates, where every value is going to have some r corresponding to it, some radius, some theta measurement that's measured from the positive x-axis, and some z coordinate determining the height from that positive or from that x and y plane. Now, when we do this, we're going to have to recall a few things from polar coordinates. All right, so I'm going to write this in orange, and again, this is all just recall, and this is going to be from polar coordinates. Every x coordinate can be thought of as r cosine theta. Every y coordinate can be thought of as r sine theta. We can also have this Pythagorean identity that says x squared plus y squared is equal to r squared. And we also have that tangent of theta is given by y over x. Now, we want to use all of this because when we're trying to, let's say, convert from a rectangular system, from those x's and y's, could we then interpret all those x's, y's, and z's in terms of polar coordinates, or in this case, cylindrical coordinates? That way we can extract what is our radius, what is our theta, and finally what is our z. In that process, what we're doing is we're generating these specific cylindrical wedges. Using these cylindrical wedges, we're going to be able to integrate over this given volume. Given some change in radii, given some change in z's, and then given some change in thetas, we're going to be able to identify what are all of those changes happening, or how are all of those changes happening in terms of cylindrical coordinates. Now, I want to give you more of a better demonstration on this. So instead of looking at this statically, we're going to look at this dynamically and see how we can actually produce these results. For that, I want to turn to my friend GeoGebra. So follow me along. All right, here I have GeoGebra, and here we're going to be working with these cylindrical coordinates. So looking at these cylindrical coordinates, what I'm going to do here is let's reorient this. There we go. For our view, we have our x coordinate, our y coordinate, and then our z coordinate here. And what I'm going to do is on the left hand side over here, I've created some sliders that I want to move here. I'm just going to move some of these. There we are. Let's change the height a little bit more. Let's make this less. There we are. All right, so as you can see, this cylinder here is carving out some volume. Now, as we change the angle of rotation, again, remember, that angle of rotation was based off of the positive x-axis. So as we start moving this angle of rotation to do a full circle, call it 2 pi, what it's doing is it's getting us this closed-in cylinder. If we change the height, all it's going to do is it's going to change the height of this cylinder, whether we want it to be a small cylinder or a large cylinder. The radii will then determine what is the radius of this cylinder. Do we want the cylinder small to have a big radius? Or are we just looking at some sort of cylindrical wedge that we need to integrate over? And that's what this process gives us. That's what this method is going to help us adjust, is whenever we are integrating over these cylindrical wedges, under the Cartesian or under the rectangular system, it becomes rather difficult because some of these functions are going to be square root functions that we then need to evaluate, which integrating square root functions can get a little bit tedious. So in order to avoid that tedious aspect or to find a workaround, we analyze them using these cylindrical wedges, and therefore we're going to be able to find that integration rather easily, or a little bit more straightforward. So again, this applet is on GeoGebra under our course, so you can go through and you can view it and you could play around with it, change all of these heights, change the different dimensions to see how we're producing this and how theta is going to depend on r, and the height is then just going to change your given values for these cylinders. All right, so again, we want these cylindrical wedges. Sometimes it's only this one cylindrical wedge that we look at in quadrant 1, and that's perfectly fine, because here the theta values are just going from 0 to pi halves, the radii is just going from 0 to 5, and then the height is just going from 0 to 4, which means we're going to be able to extract just our bounds, or we were able to extract our bounds to be numerical bounds instead of bounds that have functions in them. All right, so let's go back and let's start writing this up a little bit more nice. That way we can get how we're going to work with these triple integrals in these new founded cylindrical coordinates. So let's go back to the class. All right, so this is what this little picture here was denoting, was that we wanted to find all those changes for these cylindrical wedges. Now, as we start looking at this, right down here, I have this sort of definition or this process that we're going to be working with. If we have some region E bounded in R space 3, where we consider the domain x's and y's, and we consider some functions to be bounding those z values. So those z values don't necessarily need to be bounded by the x and y plane. We could actually move that to say it should be some, let's say, plane, which will be, I don't know, let's call it z is equal to 2, and that will then create this lower plane that we look at, or this lower surface, and this upper surface. So these z values are then bounded by these two different functions that are determined by x's and y's. Now, if we then want to transfer all of this into cylindrical coordinates, then we're going to need some r's, some thetas, and some z's to do our business. Thetas are going to be bounded between some alpha and some beta. So again, this theta value could just be bounded between two angle values, and that's what this picture here shows. That this value that is sweeping through, this wedge is sweeping through, that's our d theta. Which means this here could be some alpha, and this over here could be some beta angles. All right. Now, once we have identified that, then we can go through our radii. What are the two radii functions? Well, the two radii functions, we could consider this radii out here to be, let's say, h sub 2. Excuse me there. H sub 2 in terms of theta, and this here radii to be h1 of theta. And then all we need is just heights. those heights, u1 and u2, can then just be thought of as these surfaces that are bounding from below and bounding from above. This up here could be our u2 value, and this down here could be our u1 value. And in that sense, as long as we account for the thetas, for the radius, and for the heights that are changing, we will be able to convert any triple integral in rectangular coordinate system into a triple integral using cylindrical coordinates. When we do so, we must always account for our integration, or our let's call these our constants of integration. All right, these constants of integration, when we go from cylindrical or Cartesian to cylindrical, these are always going to be thought of as r dz dr d theta. And again, this kind of goes back into the same process that we looked at when we were talking about polar coordinates and we were doing double integrals in those polar coordinates. All right, so now that we have this going for us, let's see if we can identify a few items here. All right, so here we go. On this example, we want to identify the surface for each of the following equations. Part A. We're going to be looking at r is equal to 5. Part B, we're going to be looking at r squared plus z squared is equal to 100. And part C, we're going to be looking at z is equal to r. So let's see what we're looking at here. All right, see if we can try to identify what we have. All right, so r is equal to 5. In this case, all we're doing is we're creating a radii, or a radius. Because we don't have anything else in terms of theta or in terms of z, that's going to mean that theta and z are allowed to be anything that they can be. The only thing that we have at our restriction is that r is equal to 5. Which means at every single point that we want to account for, we have r is equal to 5. This should signify that we have some sort of cylinder that we're working with. Now, if talking through it's a little bit rough, then that's fine. We can look at this algebraically. So let's look at this algebraically then. R, according to the work that we have up here, look at this part in orange here. I want to get that, which means could I consider r squared? And if so, what is r squared? Well, that's just 25. But isn't, by the process that we just saw up here, r squared, isn't that just x squared plus y squared is equal to 25? So what is this equation of in terms of a rectangular coordinate system? Yeah, that's going to be our cylinder with radius of 5. Awesome. All right, so here, as we can see, we have this cylinder. Oops, excuse me. Cylinder of radius 5. Nice. All right, so let's look at the second one. Let's look at part B. For part B, we have r squared plus z squared is equal to 100. Now, under the assumptions that we have up here, we know that r squared is equal to x squared plus y squared, which then means that this r squared can be thought of as x squared plus y squared. That's for this piece here. And then we still have this plus z squared, which means this here, this r squared plus z squared is equal to 100, is really just a sphere of radius 10. That's it. So anytime we see r squared plus z squared is equal to some number, we can just think about it as some sort of sphere. Now, the last one, when we're looking at z is equal to r, when z is equal to r, what we can think about is this here, that when we have this, this R value is just the square root of x squared plus y squared. And in that sense, this is just z is equal to x squared plus y squared. Square root of x squared plus y squared. This here is a cone. Now, again, we have all of these different interpretations. Again, z is equal to r, and then r squared plus z squared is equal to 100, and then r is equal to 5. Anytime that we have all these different interpretations, we could then, again, think about them logically, or we can go through and think about them algebraically to try to extract what it is that we are observing. All right, now let's see if we can start using this to build some examples of triple integrals in R space 3. So here's your example. We want to evaluate this triple integral over the region E for y dv, and this is going to be where E is the region that lies below the plane, z is equal to x plus 2, there we are, above the xy plane, and between the cylinders x squared plus y squared is equal to 1, and x squared plus y squared is equal to 4. Alright, so we want to again evaluate this given triple integral where we have some bounded region E that we will be integrating over. That bounded region is then going to be given by these planes, by the plane z is equal to x plus 2, and that's going to be above the x and y plane, and then it's going to be between the cylinders x squared plus y squared, and x squared plus y squared is equal to 4. So again, we have these two cylinders that are being bounded, and these two cylinders being bounded by the x and y plane and some sort of plane up above. All right, so I'm going to give you a really quick interpretation of what this looks like. All right, because again, we don't always have this technology available to us, and we have to try to get some type of spatial reasoning to make sense. That way we can try to dissect what it is that we're going to be integrating. All right, so here's my interpretation of what we have going on. That I have some sort of cylinder here. Oops, let me go ahead and start this over again. Here we go. Have some sort of cylinder taking place. All right, there we are. This cylinder is going to extract to the top like that. The plane is then going to slice both of these cylinders like such, and we have some sort of inside cylinder. There we are. So this is my interpretation of what is happening. That we have this plane that is slicing through, and that plane is at z is equal to x plus 2. And then we also have this cylinder, this inner cylinder, which is x squared plus y squared is equal to 1, and this outer cylinder, which is x squared plus y squared is equal to 4. And then we have this bottom part down here, which is this x and y plane. All right, so we now have to start thinking about this in terms of polar coordinates, or in this case, cylindrical coordinates. Now, if we're looking at cylindrical coordinates, then we have to interpret a few things. We have to interpret what is r, so we need to find what the bounds for r are going to be. Find bounds for the radius. In other words, the radii. We need to find bounds for theta. All right, and then we can also find bounds for the z values, and that's going to be the heights. Find bounds for z, in other words, heights. Now, z is the one that's easiest to think about because the bottom one here is z is equal to 0, because again, that's the x and y plane. The top one's a little bit the one that's different. This one is actually z is equal to x plus 2. Again, so that's not too bad. The z heights aren't the bad parts here. That's actually the really good part that we have. We have this plane up here, so that's not too bad. And we have this bounded region down here, which will be that x and y plane. There we are. Now, within all of this, we have to then interpret in terms of polar coordinates. So we're going to transfer this x into polar coordinates, which means x must be r cosine theta. That's the x value, and then we have plus 2. Z is equal to 0 is going to stay as is. All right, not too bad. Now let's see if we can find, so the bounds for z are done. Let's see if we can find the bounds for theta. All right, so the bounds for theta. Now, this is a complete cylinder, which means if we start at the positive x-axis, here we go, starting at the positive x-axis here, what angles is this sweeping through? Well, if it starts at the positive x-axis, then naturally it's going to extend through to theta, which means theta needs to go between 0 and 2 pi at all times, which means we just found the bounds for theta. Now the radii. What radii is this going to extend through? So the radii that's extending through needs to be this radii at all times. That radii goes from a radius of 1 to a radius of 2, which means r goes from the radius from 1 to 2. All right, that's not too bad. That's actually looking pretty good, and we found them. So let's go through and let's set this up. The triple integral for y dv now then is going to become the triple integral. Instead of y, we're going to have our cylindrical coordinates, which means this y value is then going to be r sine theta. Now remember what dv is. dv in terms of cylindrical coordinates is your r dz dr d theta. So in here, instead of having dv, we're going to go through that r dz dr d theta values, and we're going to go through and we're going to say, okay, our z values, well, they go between 0 and r cosine of theta plus 2. The r values, the radii, the innermost integral, or sorry, the middlemost integral, that's our r values, they go from 1 to 2, as we found. So they go from 1 to 2. And then lastly, our theta values, the thetas sweep between 0 to 2 pi. Which means all we have to do is evaluate this integral. So let's go through and let's evaluate this integral. Here we go. Outermost is 0 to 2 pi. There we are. Middlemost is from 1 to 2. And we're integrating the integrand here, which is r squared sine theta with respect to z, which means this is going to be r squared sine of theta multiplied by z, and that's going to be evaluated from 0 to r cosine theta plus 2, and that's going to be dr d theta. All right, going through 0 to 2 pi, and then 1 to 2. Let's evaluate for z. Remember, everything else is a constant, so right now z, so this is r squared multiplied by sine of theta multiplied by r cosine theta plus 2, and then we subtract 0, but 0 is just going to go away. So that's dr d theta. Alright, that's looking pretty good. Alright, this is from 1 to 2, and I'm going to distribute here, so this is going to be r cubed sine theta cosine theta plus 2 r squared sine theta, and that's all dr d theta. Alright, so now all I need to do is evaluate this for this integral. Alright, so let's evaluate this using r's. So we're going to integrate with respect to r. So this will now be 1/4 r to the 4th sine theta cosine theta plus, in here this is going to be 2/3, and I don't like the way that 2 looks, so that's going to be fine. So that's going to be 2/3 r cubed, and that's going to be sine theta, and this is evaluated from 1 to 2, and that's going to be d theta. Alright, looking promising so far. So let's keep this going. Let's work right up here. This is going to be the integral from 0 to 2 pi. There we go, from 0 to 2 pi. And let me see now, we're going to have this 1/4. So this 1/4 here is going to be evaluated with that 2. So that's going to be 2 to the power of 4. And then we're going to divide by 4, which should get us just 4. So that's going to be 4 sine theta cosine theta plus, here we're going to have 2/3 multiplied by 2 cubed. Now 2 cubed, that's going to be 8, so then 8 times 2, that's going to be 16, so then 16 divided by 3 is just 16/3 sine theta minus, then we're going to subtract this term here evaluated at 1, so that's just going to be 1/4 sine theta cosine theta minus, once again, evaluated at 1, that's going to be that 2/3 sine theta, and this is all with respect to theta. There we are. Alright, we have some like terms, so let's go ahead and let's combine those like terms before we integrate. So sine theta, cosine theta, sine theta, cosine theta, let's go ahead and combine them. Alright, this is going to be 4/4, so that's going to be 15/4 sine theta, cosine theta. Alright, not too bad. Alright, let's keep going. The next one's going to be 16/3 theta minus 2/3 theta, so that's going to be 14/3 plus 14/3 sine theta. There we are, and that's d theta. Alright, so all we need to do is evaluate this, and then we'd be done. So let's see if we can evaluate this. Alright, now you can go through this one here, and you can use a u substitution. If I believe you capture sine of theta, you should be able to do this with a u substitution. And in here should be just a direct substitution or direct integration, and we should be able to get it. Alright, so I will leave that up to you. Alright, so put pause, make sure that you can carry out those calculations, and then we'll go through in just a bit. Alright, so when everything's said and done, you should get an evaluation of 0. Alright, awesome. So this is the way that we work with these particular integrals when we're trying to evaluate them using cylindrical coordinates. And again, all of this is going to depend on the domain that we want to observe. If the domain can be interpreted in terms of polar coordinates, then we go ahead and we use cylindrical coordinates to make that evaluation for that triple integral. Now, the very last question that we're going to work with for now is going to be to convert this triple integral, 1 minus y squared, there we go, integral for x squared plus y squared, and then this is the square root of, whoops, of x squared plus y squared, and this is going to be for x, y, z in terms of dz, dx, dy, and we want to convert this into an integral in cylindrical coordinates. So let's convert this integral into an integral using cylindrical coordinates. Now, as you're going to see, we have a lot of rectangular coordinates values given to us, and naturally, if we go through this evaluation using rectangular coordinates, it's going to get really, really rough. So instead, what we're going to do is we're going to convert all of this. All right, so within our conversion, what I'm going to do is I'm going to start extracting what we know. All right, so what we know here is that your y values are changing between -1 and 1. So that extraction then looks like this, that your y values are changing between -1 and 1. Your x values are changing with this integral here. So your x values are then changing between 0 and the square root of 1 minus y squared. And then finally, we have that our z values are changing with this integral. So the z values that we look at, they're changing between x squared plus y squared all the way up to the square root of x squared plus y squared. Now, we're going to make a quick interpretation here. The z values are actually going to be the easiest ones to work with. And the reason I say that is because we have this to work with. Now, if we have this to work with, this actually builds a bridge from rectangular over to polar, or rectangular over to cylindrical, which then tells us that using this manipulation, this is going to be r squared, and this is going to be just r. All right, so that's not too bad. All right, that's looking pretty good. All right, now let's keep working with this. All right, let's start looking at these values here. All right, these are going to be a little bit more interesting to work with, or a little bit more difficult to work with rather than just the z values. Z values are pretty straightforward. Now, in order for us to be able to move forward from here, what we're going to need to do is we're going to need to draw this domain. All right, so what I'm going to interpret this as in this particular case is this here is going to be producing my domain. All right, so this is going to give me my domain. And I want to sketch it. All right, now the sketching here is going to come from my x's and my y's. All right, more specifically, I want to look at what this looks like here. All right, so I'm going to start extracting this. X is equal to 0. So x is equal to 0. Would you agree that's just a vertical line? All right, not bad, just a vertical line. All right, and then the next one over here, this is going to be that x is equal to the square root of 1 minus y squared. Now, that itself is just a portion of a circle. Well, let's go see what kind of circle that is. Look at that. It's just a circle centered at 0, 0, which gives us a radius of 1. So, let me try to sketch this out, and that way we can start extracting what we need. All right. So this is my y, and this is my x. Now, according to this, I have a circle, but it's not an entire circle. This means that my x values are only bounded between 0 and this portion of the circle. Now, again, this is a circle of radius 1, but since it's only bounded where x values are greater than 0, that means this is only bounded in quadrants 1 and quadrants 4. So my circle then looks like this. Now, I'm hoping you all can make a better circle than I did. All right, there we go. That's my better attempt at it. Now, does this fall in line with my y values? Well, my y values are between 1 and -1, which naturally means that the domain that I'm looking at is right in here. This is that domain. Nice. So that again follows this y values being bounded between -1 and 1, and that follows the x values being bounded between 0 and the top or the side half of this circle here. Awesome. So now that I have this specific integral, I can now talk about setting it up in terms of polar coordinates. Or, sorry, cylindrical coordinates. I keep calling it polar coordinates. They're interchangeable. So this was -1 to 1. And this was from 0 all the way to 1 square root of 1 minus y squared. Then the integral from x squared plus y squared to the square root of x squared plus y squared. And this was for x, y, z being dz, dx, and then dy. All right, so let's go through the integral now. I have a triple integral. All right, I'll worry about the bounds in just a little bit. What I want to focus on right now is going to be this integrand, this x, y, and z. So interpreting that x, y, and z in terms of cylindrical coordinates, x is always going to be r cosine theta, y is always going to be r sine theta, z is just z itself, and then I need my dz, dx, dy. In terms of polar coordinates, or sorry, cylindrical coordinates, we always remember that dv must always be r dz dr d theta, which means here we need r dz dr d theta. Nice. So let's go through and let's find our dz's. dz's, like we said, changes in z's was from r squared, moving all the way up to just r. Our radii, the radii is going to be the radii for this domain. So the radii for this domain, what radii does it sweep through? Well, the radii is sweeping from 0 all the way out. So from 0 all the way out to these values. And it keeps sweeping all the way out, which means the radii is going from 0 to 1. Now thetas. What are the thetas sweeping through for this domain? Well, the thetas start down here and they sweep in a counterclockwise direction, which means they start at negative pi halves and they sweep all the way to pi halves. There we are. All we have to do is just clean it up a bit, which means this is going to be the outer integral goes from negative pi halves over to pi halves. The middlemost integral goes from 0 to 1. The innermost integral goes from r squared to r. And this is all going to be r cubed. Yes, r cubed sine theta cosine theta multiplied by z. And that's going to be dz dr d theta. This integral here is way easier to evaluate than the initial integral that was given to us. And this is how, again, we work with cylindrical coordinates. Now, in the next video, we're going to talk about spherical coordinates and how we work with those. All right, so stay tuned for that, and I will see you all soon.